Yeah, the streaming is started.
Okay. How to send the address?
I'm trying to do this. Yes, the streaming starts.
I can confirm that it's working.
Okay, so you are watching on YouTube?
Let me see.
It could be seen with little bit of delay.
Okay. So I will start in 1 minute. People are joining.
Probably people after lunch break will join us a bit later, because I see 20 people for plenary sessions, not too much, and a average number for such sessions are over 50. So this is,
Yeah.
but this is a quite let's say different topic than power electronics, but this is also interesting in case of future applications of power electronics. So maybe some people will be interested.
Yeah. But the thing with this online, that people join when they want, and because they are not in the room. Okay, I guess we can start. It is 4 p.m.
And the second co-chair is with us or not?
I don't see Ilhami.
Yeah.
I don't see Ilhami.
Maybe we'll join.
Yeah, maybe he will join later. I can start, Marius?
Babak, you are boss here, not me.
Okay. Thank you, Marius. So good afternoon, everyone. Thanks for joining us in this keynote session. The keynote speaker is Dr. Jean Lévêque from University of Lorraine, France. And the presentation is entitled Superconducting Machines for Aircraft Applications. Dr. Lévêque worked about 30 years on superconducting components and their applications in electric machine design and current limiter. And recently he worked with aircraft industry for future electric aircrafts. And I think he collaborated with Safran Group in France. I think he will talk about this in his presentation. Jean, you can start.
Okay, thanks, Roman. Ladies and gentlemen, I don't know exactly who is here. Hello, by very beautiful weather in Nancy. And today my talk is dedicated to the application of superconducting motors or generators in the field of aeronautics. And I will start this talk by a quick overview of superconducting materials and their essential properties in the field of electrical engineering, without being too long, because it's not the topics. Then I will present the different reasons that lead to think different about air transport. And then we will talk about electrification project and obviously superconducting motors and generators for aeronautics, before to conclude. So I start this part by my overview of superconductivity. Two properties are really fundamental for superconductivity. The first one discovered in 1911 in Leiden, in Holland, is a sudden drop of the resistivity below a certain temperature. This is illustrated on this picture, where the resistance of YBCO ceramic is represented. At first, the resistance decreased as linear as for classical Ohm's law for classical materials. Then it dropped sharply, very sharply to zero. So we have a possibility to obtain circuits carrying current at zero power with no losses. The second essential property, which is the true signature of the superconductivity, is a perfect diamagnetism. The material expels the magnetic fields, like you can see in these pictures. We need to be very careful with this experimentation. Generally, in this experimentation, due to heavy permanent magnet, it's generally simple and slow. As this superconductor is a perfect conductor, without resistance, it can trap magnetic flux very easily. And so we can use this property to make superconducting permanent magnets. So superconductors have three critical parameters: a critical temperature, a critical current density, and a critical magnetic field. These three parameters allow us to define a surface that we call critical surface. Above this surface, the material becomes normal, and below, it is superconducting. We also see that the lower the temperature, like that, the better is the current density. So you always take advantage to decrease the temperatures. And I give here some indicative value for the critical parameters. The critical magnetic field is between several millitesla and 100 Tesla. Critical temperature between 9K and more than 100K. And the critical current density generally below several kiloamps by square millimeters. And superconductors can be separated in two categories according to their operating temperature. On the one hand, we have low critical temperature superconductors like niobium titanium, and on the other hand, high critical temperature superconductors like YBCO ceramics. The low temperature superconductors are generally cooling by using liquid helium. And on the other hand, for high temperature superconductors, the usable temperature range is large, from about 20K to 77K, depending on the application. The lower their temperature, the better their performance. And diboride, magnesium diboride, it's a special case. But it's difficult to classify because its critical temperature is intermediate between that high and low critical temperature superconductors. And some value of parameters are given. By example, for niobium titanium, the critical temperature is about 9K, and the critical magnetic field at the temperature of 4K is about 11 Tesla. And so generally we use helium liquid to cool down this kind of superconductors. And on the other side, you can see YBCO, the most common superconductors, high temperature superconductors, second generation superconductors, where the critical temperature that's more than 90K, and the critical magnetic field upper than 50 Tesla, below 20K. And for this kind of conductors, you can only obtain very thin film, 0.1 millimeters, that we use as wire. For niobium titanium, niobium stanium, or MgB2, it's always a round wire, classical round wire. For visco tape, you can have different shape, round wire or flat ribbon. And a very important fact is the behavior of superconductors. And superconductors, contrary to classical material, have a strongly nonlinear electric field versus current density behavior law, as you can see on these pictures. It's a characterization of a superconducting wire conducted in my labs, and you can see the electric field versus the current, and you see this very special shape. And below a certain value of the current, you don't have electrical field, no measurement is possible, and so you can't have losses in this part. And the critical current is defined in a standardized way. It is a current for which an electrical field value is 1 microvolt by centimeters. As you can see, the critical value of the current in this sample is just about 40 amps, because at this point you have the critical value of the electrical field, which is defined by a normalization, which is 1 microvolt by centimeters. And if G is below GC, you can transport GC current without losses. But if we use AC current, you can generate losses, and these losses can be ranged from negligible to very, very high. That depends on the frequency, and that depends on the conductors. If G is superior to GC, losses increase exponentially, and some heat is generated, and you can destroy your sample or your coil if it is a coil. And you have here the typical behavior law for superconductors with N factor, which is very important. We determine the chart of the curve. Another essential feature for application design is the dependence of the current transport properties on the magnetic field and the angle at which it is applied to the face of a tape, the superconducting tape. We see on this curve from tests conducted at Toku University. We also see the dependence with the temperature. And you can see that if we decrease the temperature, you increase the performances. Okay? This is the ratio between the current density at a given temperature and the current density at 77 K. And you can see the angle of the magnetic field which is applied on the superconducting tape. And generally, when you design, you have two solutions. One of them, you take into account the worst case, this case, or if you don't want that, we design your application to always functioning in the best case, by example, this part. And on this last side of this overview, we see that this dependence of the, you see the dependence of the current transport properties with magnetic field, like here. You have GC, current density, and the magnetic field. And you can see here the load of application. So we have on one side of the characteristic of the superconducting wire for a given temperature, and the other side, the load line for the application. And we first define the operating point, the functioning point. So it's not exactly like a copper coil. You really need to work with the behavior with magnetic fields of your superconducting tape, and it's different for each superconducting tape, each kind of superconducting tape. Moreover, we take care to take a safety margin. So the current density is about 60 or 80% of critical current density. So this part is one of the key points when designing a superconducting winding. But in certain cases, you can increase this value and work really near the critical current. So now, after this very brief presentation of superconductivity, we will go into the heart of the matters and present the reason for the electrification of the air transport. The environmental impact, especially related to global warming and the huge increase in fuel costs, have affected transportation sector. Airlines contribute to between 2 and 4% of environmental impact today, now, including pollution, dioxide emissions, and so on. And it is expected to rise to 10 to 20 to 15% or more in the next 30 years if no major improvements are made. And so the aviation's demand is growing as environmental concern, noise emission, aircraft fuel burn, fuel length. And so we have three possible scenarios. You can see this scenario on these pictures. We take for reference the years 2005. Without any action on the red line, we will have a strong increase of dioxide emissions. With the first work on infrastructures and on technology, it's possible to limit this increase. It's a green line. And on the other hand, if we want to reduce this dioxide emission, we need a breakthrough technology. It's a blue line. And that's the impact from biofuel, by example, and radical technology like superconducting technology. You have in Europe a different program about that. Managed, by example, by the Advisory Council for Aeronautical Research in Europe, ECARE program. You have some big program in Europe. The first of one, Clean Sky, it's finished, and now Clean Sky 2. And the main objective for the years between 2020 and 2050, it's an oil reduction by 50%, fuel consumption and the dioxide emission reduction by 50%, and also a big reduction of NOx emissions by 80%. And if you just examine engine contribution, a specific fuel consumption reduction by 15 to 20% is expected. Same things for NOx emission. It's a big reduction which is expected, about 80%. Oh, what happened? Okay, let's work. And you can see on this curve from Boeing commercial airplane current product overview, the growth of air traffic since the 80s is constantly increasing. And it's likely that the crisis related to the Earth situation will not change this phenomenon in the next years. This also implies a strong increase of the pollution emissions. And that's a reason for what we think to electrification of air transportations. And on the other hand, since the 80s, the need of electricity for aircraft is constantly increasing. You can see that on this curve. You have several aircraft, civil aircraft, and you have also military aircraft like F-35. And the onboard power was hardly 200 kilowatts during 80s, and now reach the megawatts for the most recent airplane like Dreamliner. So you have a very big increase of the electricity consumption in an aircraft, and due to a lot of facilities on board, and also due to massive electrification of a lot of actuators. And so we need to think air transport of tomorrow. And as we can see before, as the aviation's demand is growing, as the concern of environment, noise emission, aircraft fuel burn, and future aircraft will be more electric with high power to mass ratio, which is important, but it's a general problem of electrification of transport, and it's not only for aircraft application. You have the same problem for train or for automotive application when we need big improvement of power to mass ratio for motors. And you have different way. The way with several megawatts on board, by example, in the different big aircraft project, N3X by NASA, with 14 5 megawatts thruster and 2 40 megawatts generators. And EasyJet also promised a few years ago commercial flight of all electric commercial flights for the next years. Or maybe at this time it's more a joke than other things, but they promise it, and I think it's a trend for the future. You have also dynamics about a few hundred kilowatts on board, but small flight, by example, for taxi flying that's designed by Uber, or taxi flying by Airbus. That's globally very similar projects. Now that's time to talk about generators and motors dedicated to the aeronautical sectors. And you have on this picture from a symposium on jet engine and gas turbine, you have on this picture a simplified view of the actuator present in an aircraft. You can see in blue was pneumatic power. you can see in red all actuators which use hydraulic power, and you have in yellow actuator using electrical power. And the goal is to use the maximum of electric actuator in the future in an aircraft, and to remove hydraulic and pneumatic actuator to use electric actuator. That's the basic line for more electric aircraft. You don't remove all the system, but part of the system to use electric actuators. And you have different configuration for the electrification of the propulsions. You can see that on this figure. By example, in these pictures, it's a case of a series hybrid solution. You have a turboshaft, that's a turbine, which is linked to a generator which produces electricity to supply different distributed motors and distributed fan, using a battery as buffer. You also have a parallel hybrid solutions. In this case, you have a battery which is not a buffer, which supplied a motor which is linked to turbofan, which use fuel and electricity for fan. That's a solution. You have also different more complex solution. By example, series of parallel partial hybrid solution. In this case, you have a turbofan, you have the fan, turbine, linked to a generator, high power generator, which supply different fan, different motors, with a buffer, always a buffer for the connected link to the generator. So in this case, you have two kinds of fan. Fan with a turbofan and electric motors with this fan. You have also an all-electric solution using battery and electric buses to supply motors and fan. This solution is more complex due to the battery, which is really heavy. And you have also some different solution without buffer to remove the important weight of the battery. It's a roadmap for 2050 years from IEEE. And so you can see on this slide different projects of more electrical aircraft. On the first table, you have the required power to mass ratio for different kinds of aircraft, from very small aircraft for commuter to very large aircraft, intercontinental flight. So you can see the different solutions, parallel hybrid, all electric, turboelectric, and you can see the specific power to mass ratio from 3 to 6.5 kilowatts by kilograms. They never specify in this case specific torque, but they always use a specific power to mass ratio. If you want more important aircraft, one faster by ICE, you have also the same requirement between 3 and 6.5 power to mass ratio. And you have also an increase of the power from 1 to 11 megawatts. And you have also the very big aircraft. By example, for Airbus A380 or jumbo jet, and generally you have 4 motors, and at this moment it's not really feasible. You need a very large specific power to mass ratio, and you can see that in a lot of cases batteries are non-available, and so it's a very big problem. And you have also on the second picture, you can see on the second table a great diversity of power and speed for this study. With power to mass ratio specified in certain cases by taking into account only the active part, and in the other case by taking into account the whole machine. And these results come from recent work on these topics, and generally it's paper design. And in this table, when they want, by example, 6.5 power to mass ratio, kilowatts by kilogram, it's for the whole system. So not for only active part, or not for a motor without shaft. By example, you have a lot of design when you have where you have an estimation of the mass and the power to mass ratio, removing shaft. And you can see here different electric aircraft projects by NASA, by Boeing, by Israel, by Rolls, and in this project you can see different speed, and also you can see the propulsion system with a partial turboelectric, and using in some time a fuel cell. And you also can see the power which is required from 3 megawatts to 50 megawatts for the biggest project, N3X, with a lot of distributed engine along the aircraft. And so, for the moment, it's a big project, not a lot of design. And you can see here different pictures of this project with nice pictures. You can see IFAN-X technology designed by Airbus, electric hybrid aircraft designed by Sunum. And you have the biggest project, that's turboelectric blended wing body, N3X. And you can see here the benefit of this kind of aircraft. You have in the first part the high life body. We lead 35% fuel reduction consumption. You can also maximize fan bypass ratio, and you can increase about 10% of the fuel reduction. You can also, by this shape, reduce drag, and you can decrease by 20% the fuel consumption. And also you have some other systems which contribute to the reduction of fuel burn. And so you can obtain reduction of consumption by more than 70%. But in this case, you have always turbine inside to produce electricity. That's not a project with embedded battery. And now, how to process to increase specific power? We have only two ways. The specific torque is proportional to the magnetic field produced by the armature and the magnetic field produced by the inductors. So first way is to increase the magnetic field produced by the armatures. Okay. In this case, you can use, by example, superconductors, and if you can have high current density, it's good. But you need to take into account AC losses and superconductors, and maybe it can be a very big problems. And you can also use cryogenic cooling for the armature with copper or aluminum coil to have a lower resistance. And if you have a lower resistance, you can remove more easily losses, and you can increase current density. And by this way, in all the case, you can use ironless housing or small back iron, and so you can obtain without iron tooth a better conductor density. The second way is to increase the magnetic field produced by the inductors. So in this case, we use superconducting wire, so you can obtain a high flux density and remove magnetic core. And we need to make that taking into account aircraft safety specification and, by example, brushless system and fast flux weakling. So we have several possibilities. One of them is to use permanent magnet motors, and in this case, we take advantage of high performances due to the rare earth permanent magnets. It's a big way of research. But the maximum flux in air gap is about 1 Tesla, and it's really difficult to suppress iron tooth in the armature due to the difficulty to increase the value of the magnetic field created by the inductors. And the main risk is to decrease a lot if you remove iron tooth magnetic field on the armature coils. So the main goal is to increase the electric load thanks a lot of thermal studies to be able to remove a maximum of losses to be able to increase the current density inside this armature coil. For superconducting motors, which is another solution, this is my study, we can use superconducting wire to obtain high flux density in the inductors and to remove magnetic core, so we can go up to 1 Tesla. And you can go to 2-3 Tesla in the air gap using ironless copper armature, by example. And in this case, it's the same problem than for permanent magnet motor. We need to increase the electric load thanks to a lot of thermal studies. You also can use ironless superconducting armature, but in this case, you have AC losses in superconducting wire. And in all this solution, you have for aircraft application, and it is the main problem, high-speed machine. And so, if you remove iron tooth, you have losses in armature coil. You have losses due to the high frequency of the current, and you have losses due to the induced current due to the armature, due to the inductors. And you have losses in the back iron if you prefer to have a back iron, and you need also to remove these losses in the back iron. And at this time, the main study for superconducting motors and generators are made generally at low speed. So even if you use full superconducting motors and superconducting tape for the armature, you have a very low frequency and so low losses. And at this time, you have a lot of research about the reduction of AC losses in superconducting tape. By example, you can reduce the size of the superconducting tape to make some things which look like to leads wire. So we need to make some assumptions, and we consider cooling between 20 and 30 K, by example, using a liquid hydrogen as a cooling liquid at 20 K. For the rotor coil, you can operate with a current density which is about 300 amps by square millimeters. It's easy to obtain it. It's not an optimistic value. It's a conservative value. In the armature, the HTA steps are subject to high frequency AC current that lead to significant AC losses. And we need to take into account this fact because it's a problem to remove these losses at very low temperature. In the armature, if we use copper, the temperature is not cold, but generally warm. And the liquid air cooling is a realistic option that can provide high current density. And HTA bulk could be considered as a potential alternative to HTA step coil to create a magnetic field in the rotor. I said in the first slide that we can make permanent superconducting permanent magnets when you can trap the magnetic flux inside a superconducting bulk, and the maximum obtained value is 17 Tesla, but that needs a very complex system. But I think that it's possible in an embedded system to obtain more than 3 Tesla. And I present, oh, sorry, I don't pass my slide, but oh, that's important. So I present now some historic view of the project. And the first superconducting alternator is made at the beginning of 60s, and it is made for aircraft application at this time. And in 70s, you can see Westinghouse project, 5 megawatt at 4 Kelvin. And during 80s, you have an increase of the power, 20 megawatt, 4 Kelvin for one part of the coil, 8 Kelvin for the other part. And after, you have the revolution of the high temperature superconductors, and we begin a new type of project. And in 90s, you can see 1 megawatt project. We reduce the power, but use a more convenient cooling system for superconductors at 20 K. And after the biggest project of motors in 2000 years, that's a project by General Electric, about 40 megawatts propeller for marine application at 100 RPM at 20 Kelvin. And many years after, some applications are dedicated to aircraft applications. And I present several projects for aircraft application. By example, you have a SUM project, which is a project we found from Europe. And you can see a consortium with Oswald, a German company, Airbus, Cambridge University, Rolls-Royce, KIT in Germany, Superox in Moscow, and Air Liquide for the cooling system. And you see the mock-up of this design. And if that's a design for 1 megawatt thruster, 6,000 RPM, with a conceptual design about 20 kilowatts by kilogram. And they made a lot of experimentation on this project. Another project which is designed by
Jean,
oui?
2 minutes left.
Oh, 2 minutes.
Yeah.
Okay, it's very short. I'm sorry. Okay, when I prepared, I take less time. Okay. This is project designed by Air Force Research Laboratory, 1.3 megawatts, 10,000 RPM. And you can see a drawing, the experimentation here. And it's a homopolar machine with a stator yoke and armature wingings and a stationary coil here. And you have a solid part in iron, which is magnetized by this stationary HTS coil, like in a claw pulse system. This system has a good functioning and is designed especially for aircraft. And you have here the most accomplished project by Moscow Aviation Institute. So it's a Yak 40, 500 kilowatts, 5,000 RPM. You have here the superconducting motors. It's a 3-reactor aircraft. You can see here this aircraft, 2 of the 3 reactors, and they put on the nose of the aircraft, they remove the classical nose, then they put a nose with a fan and the superconducting motors, and now we made tests inside Siberia. So I don't have any sufficient time, but I go directly to the end of my presentation. That's a topology of the flux modulation superconducting motors, which made in my university. And it's I go directly to the end. It's a project, 50 kilowatts project, and now we increase this project to 100 in the first way. And we have a second one project, 500 kilowatts at 5,000 RPM. You can see the superconducting motors here, this pipe for the cooling down the superconducting motors. And here, this is my superconducting motors on the bench with this classical generators for test. And this motors is about 50 kilowatts. We increase the power to 100 kilowatts, and this motors is about 40 kilowatts. In this case, you have less than 50 kilograms. In this case, 300 kilograms. Okay, but this motor is not an optimism motor. So now I conclude. And to conclude, further works on our project is to design and build a 500 kilowatt thruster. We began now. It's probably finished in more than 1 year, and also finished all tests on the 50 kilowatts machine to continue to increase power. You can double easily the increase the power. And so the development of electrical and particularly in superconducting architectures require particularly important challenge for aircraft application. And in this case, a lot of collaboration and commitment is needed from equipment manufacturer, by example, and also from HTS tape manufacturer, which need to design specific superconducting tape for aircraft application and also end user. And for the moment, we have some grant from Europe, and so it's convenient for us. And so I am really sorry for the time and for the delay.
Thanks so much, Jean. Of course, it was very interesting, and you covered so many topics related to superconducting machines. We have time for 2 questions, and maybe through them we will be able to come back to some slides that you couldn't show.
Yes.
Stan, you can go ahead.
Okay, just a very quick question, because of this lawyer of the devil that I'm always very much glad to do. The weight of this motor with the cooling technique, all this is connected to keep the temperature. You say 20K, or it is high temperature semiconductor. Then the price of the high temperature superconductor tape, which is quite expensive even to compare with anything that is making more and more higher the price. So please compare the classical, because the 36 megawatt which you show on the picture, I know that was considered for some frigates in the United Kingdom, and they bought just normal 25 megawatt normal machines for the frigates. Just a question of how it is going to be lower as price, lower as weight, and more safer, especially when it is the talk about the military airplane.
Okay, okay. We think 20K because the trend is to use liquid hydrogen as a fuel. And so, as we have liquid hydrogen, you have very low temperature.
Very low, yeah.
So we can use its very low temperature to cool down a superconducting motor. And now we build a partial superconducting motors using leads wire for the armature and the superconducting tape for the inductors. And at this time, the superconducting tape has exactly the same cost that leads wire. To avoid, and we need to use leads wire to avoid too many losses, and too many losses also due to eddy current because we have no iron tooth in the armature. And so, okay, the cost is important for HTS tape, but not only for HTS tape. The cost of leads copper coil is also very important. And the main problem for HTS tape, it's not exactly only the cost. The main problem is that the weight of the superconducting tape is 4 millimeters. And if we want to reduce AC losses to use, by example, superconducting tape in the armature, you need to have 0.1 millimeter for the width of the superconducting tape, and it's, for the moment, it's very difficult to obtain.
Okay, thank you.
I have more questions for later. Yeah.
Yeah, you can discuss with John, Stan. We have time for a very last question, short last question. You can unmute yourself and ask your question, if there is any. Or if you have one more, Stan, you can go.
Okay, then it is about the high frequency and the superconductivity, because I'm trying to use that for wireless transport of energy, especially when it is for the space, it's not so difficult. But when we are going to a normal freezer here to make it on a normal situation of 20 degrees of Celsius, then it is quite a problem because your superconductive material is not very, these materials, they don't like very much the high frequency. Normally, the most, which I know from my Chinese colleagues, the most higher frequency is 20 kilohertz. If you use a power converter for controlling this, probably you will need a lot of more supply of hydrogen, the liquid hydrogen. So what do we see in this?
I don't understand really. In
the high frequency is used by the converter. You have a power converter to control the motor.
Yes.
You have a high frequency inside.
Yes, sure. Yes, sure. You have a high frequency power converter. So in this case, you have a lot of probably harmonics inside the armatures. Okay?
Exactly.
So you have two ways. If you armature, it's a copper armature. The problem is a classical problem of electrification, and you have many losses, and you need to remove these losses. And if you combine no iron tooth and high frequency harmonics, you really need Litz wire, which is expensive. If you want to use superconducting tape for the armature, it's really very complex, but because you need a filter. If you have a lot of high frequency harmonics, you have too much losses, and it's really difficult.
Yes, yes, I got it.
I think that probably it's a better way to use high performances conductor, like by example, aluminium at very low temperature. It's not a superconductor, but you have a very, very big decrease of the resistance. If it's a very pure aluminium, you have, I think it's about 500 less than the resistance at the room temperature. And if you cool down aluminium, you can increase the current density because you can increase you can remove more losses.
Yeah.
Thank you.
Thank you.
Thank you, Jean. Thank you, Stan, for your good questions. And thanks, everyone, for attending this keynote. We have another keynote in 5 minutes, a student and young professional keynote. I invite you to join that keynote in just 5 minutes. Thank you.
Yeah, but maybe small announcement because we have
Go ahead, Marius.
We have to change, let's say, change Zoom session because our staff has to change sometimes. So now this session we will close, and please go to the another link in the program which is devoted for student keynote and their own table after that. So next sessions will be on the same Zoom, but this one we will close now. So thank you for your attendance here. Thank you very much. Thank you.
Many thanks. So now you close the sessions.
We close the session, but you can continue with round table at the second session in the program which is visible. So just change Zoom session.
Okay.
Thank you.
Thank you. Bon, ça va?
Thank you.
Pourquoi?
Parce que